Hello students. So we are into chapter 7 and in the last lecture we studied Bode diagrams. So we are into the frequency response of a control system, and why we need that? We need that because we can design control system based on that. We can analyze also whether the system is for example is stable or not. Yeah, so Bode diagram for first order system, yesterday I drew this for this one, right? So if your transfer function Ts equal to this one, for that the diagram Bode plot that we looked at was this is like you have the first 20 log this that you are going to plot this which looks like it will go like this, and from here it will go like this. You can approximately you can draw like this one, where here we had 1 and for omega, so because this tj omega, so where t as a function of j I omega, what I mean is sometimes you also have j written instead of I, so t I omega. Yeah, okay, so here we had 1 and so on. Actual the plot will look like something like this. Yeah, okay, so here it is 1, but general purpose for a first order system, if you want to write, this will be t equal to 1 over tau s plus 1. So this will be 1 over I omega plus 1, and for this t I omega will be 1 plus I tau omega plus 1. So basically then, even if you take example of a typical first order system, something like this, which transfer function is given like this one, same thing can be used. So instead of you have only omega here, here you have omega times t as well. So you can replace omega with omega t, that's it. And then instead of this one, you are now plotting this one, right? So you're just writing omega tau equal to like that. Yeah, or simply you can write the omega t is like this one. This is here, or you can write omega equal to 1 over tau here. Yeah, either you can write omega tau is equal to 1, or you write omega equal to 1 over tau. So right, so if you have omega here, you write here omega equal to 1 over tau. Yeah, and rest will be all, it will look like the same one as earlier. And similarly here, it will start from around 0, and at this location this will be 45 degree, and then this will be 90 degree. Yeah, so here it will be omega equal to 1 over tau. You have omega here, and here you have a phase. Phase means angle of t I omega, right? That's what that is. Okay, just here what we did, we just studied what for a general first order system how the Bode plots will look like. Okay, for the second order system we studied a proper transfer function for a second order system. Okay, so where Ts was omega n square over s square plus 2 zeta omega n s plus omega n square, and t I omega will be given by omega n square over minus omega square omega square plus 2 I, or just write I in the beginning itself, so I, and then 2 zeta omega n omega plus omega n square, right? And the plot looks like something like this. So we had like this one. We plotted omega over omega n, or you can just, since this is omega, you can also write omega here. You can write omega n where we have the resonance, or you can write omega over omega n as well. And then what we had, so we had something like this one, and then here for different zeta we had different plots, right? Yeah, for different zeta we had different plot. Similarly for here we are plotting 20 log, yeah, and then t I omega, right? Okay. Here we are plotting angle of t I omega, right? And how it looked like, you started from almost 0, yeah, and then at this point this became 90 degree, yeah. So let us say if this is minus 90 degree, so started like this 90 degree, and then when omega is infinity, that becomes minus 180 degree. Of course, here also for different zeta the value will be different, yeah. So if zeta is 0, yeah, in that case it will just go from here to here and then switch, like immediately from 0 it will go to minus 180 degree. That we have seen, all right. So if you have a spring mass system, this is Km, there is no damper here, and then what happens? Before the resonance the phase is 0 degree, after the resonance phase is 180 degree, yeah, it just switches. So this one is for zeta equal to 0. So these things we have studied already during the vibration class, right? So you can relate here, yeah. So then you have a very small zeta, it will be like this one. Let us say this is zeta equal to 0.1 and so on, right? This will be, let us say, zeta equal to 0.5 and so on, right? So here the idea is to know that for different zeta you have different curve. That's important to note. Yeah. Okay. Yesterday I just plotted just only one, so for the lack of time, so that's why I'm repeating today. There is another kind of plot which is important and which is known as polar plots. Okay. Polar plots, so unlike the Bode plot, Bode diagrams, where you plot it with respect to omega, here omega is varied and we plot, well, instead of having two separate plots, we combine both the things and make only one. That's the main idea, yeah. So how do you do that? So we vary, so we have a transfer function, let us say t I omega, right? So some transfer function, we put s equal to I omega, yeah, some transfer function, we put s equal to I omega, and then we have that, and we know that these two things are important, right? So one is this and then this one. All these are important and we will see more when we go to stability. Right now we are just understanding how to plot them, but they have relevance, that's why we are doing that. Now the polar plots, if you see, we have to plot, let us say, and then how will we do that? Okay, so let us say this one has, we want to plot both of them. We have to plot the angle and we have to also plot the the magnitude. Yeah. So magnitude, let us say we can plot like this. Magnitude will be plotted like this one. The value, the length of that will be the magnitude. Okay, this will be T I omega. This will be the magnitude. The angle here, this, yeah, this will be the phi. Yes? So this will be phi equal to angle T I omega. Yeah? So basically it is like we have S plane, right? We have S plane, and in S plane we have a sigma here, and then you have I omega here, right? So and then you have there also the value from here to here. It tells you the root under sigma square plus omega square, right? So this is the magnitude. And angle here is nothing but tan inverse omega over sigma, right? So in this is S plane. This you can call it as TS plane, right? So let's call it Ti omega plane, right? Ti omega plane. Okay, and because of that, what do we have? This axis will be real of Ti omega, and this axis will be the imaginary path of Ti omega, right? We are mapping it. Yeah? You can also call it, this is a mapping basically from actually it is not exactly mapping. Here from mapping will come later on. I will delete that. It's not mapping actually. Yeah. So but what I mean to say that whatever you are doing it, you can think in terms of that also. Here S is a complex, right? So S is a complex number, right? And here Ti omega is also a complex number, right? Complex number. So as you show S here on S plane, similarly we can show Ti omega as Ti omega plane. Here as a point, there's some point S, distance from here to here is root sigma square plus omega square, or simply is equal to simply this. Yeah? An angle is simply the imaginary part over the real part. Same thing will be here only. Only thing is you are plotting S there, and hence plotting S on the S plane. Now you are plotting Ti omega on Ti omega plane, or we can call it also G I omega plane, right? So in your textbook, instead of using T, in your textbook it is G written, Gi omega typically, instead of, or Gs you write that. Yeah, so I'm just writing T here, but which is the same thing. Okay. Now let us say the transfer function is, okay, I'm writing now instead of Ts, let's call it Gs, right? Equal, okay, Gs equal to 1 over S. Okay, in your book you have Gs, so remember that whenever I say Ts, G doesn't matter. Okay, as long as you understand what that is, that will be enough. Okay, so let us say we have this one like this, which will be integrator, right? So you know that integrator will look like this. Okay, now we want to plot it. Plot what? Plot the polar diagram. So how will we do it? So first we have Gi omega equal to 1 over I omega. Yeah. Okay. Now what is the meaning of that? So we can write minus I omega and then multiplied by minus I omega, and you have this omega square. Or simply we get equal to 1 over minus I over omega will be 1 over omega, right? And then you have minus I. Okay, so you can write in terms of angle also, right? So is equal to 1 over omega, and what is the angle here, right? Angle will be, we can also write like this one, cos the value is 0, so not cos directly, let's write 0 here, 0 minus I, right? So what is the value of tan theta here, we can find out, right? So, or you can write equal to, since it's a 0, so you can also write 1 over omega, and then 0 plus 0, since it is 0, here it is minus 1, and here it's supposed to be cos, here it is sine, right? So when it what is the value, what should be the value that that will be correspond to? So that will be 1 over omega, and then here it should be cos minus 90 degree, then plus I sine minus 90 degree will make this, right? So sine minus 90 degree is minus 1, cos minus 90 degree equal to 0. So we are getting that this is how it should be, or simply it will be 1 over omega. Angle is minus 90 degrees simply. So what we see here, angle is constant, and this amplitude is changing. Yeah, so we can say that our this G is equal to 1 over omega, right? And angle of G I omega is equal to minus 90 degree, right? So let's write here G I omega like this. Now only thing we have is to plot it, and how we plot. So we will have the real part of Z, so we can write here real Z I omega, real of that, and here it will be imaginary of Z I omega, and then minus 90 degree is, so this is the phi 0 degree, 90 degree, minus or 180 degree or minus 180 degree. This is minus, this will be the minus 90 degree. So all the things has to be on this line. When omega equal to 0, you see it becomes infinity. Yeah, so that means omega equal to 0 will be, omega will equal to 0 will be in infinity somewhere, and when it comes to omega equal to infinity, then you have this equal to 0. So the value moves from here to here, right? So we can show it like this. What I meant is like this. We have like this. Yeah. So infinity here. So omega equal to 0 in infinity, and here it will be omega equal to infinity. At this point, this will be omega equal to infinity at 0 point. Yeah. So that means the magnitude is 0 when omega is infinity, magnitude is infinite when omega equal to is 0, right? So this is how, again I have given an arrow here, meaning that this is the direction of increase in omega. Yeah, so from omega equal to 0 to omega equal to infinity. So this is how the plot will look like. Now let's look at the first order system. So system will look like GS. Okay, GS is equal to, let us say this is 1 over tau s plus 1. This is first order system. and hence g I omega is given by 1 over, and then you have I omega tau plus 1. Yeah, and which is equal to I. So let's write this way. So will be 1 minus I omega tau divided by 1 plus omega square tau square. Yeah, and hence we can write is equal to 1 over 1 plus omega square tau square minus I omega tau over 1 plus omega square tau square. Okay, now this we have to plot, and how it will look like. So we have the Bode plot for that. Yeah, we know the Bode plot. Based on that we can also have the idea. So basically that is equal to what is the if we take the magnitude of that. So magnitude we can also write something like g I omega. Magnitude of that will be here, see here, 1. From this we can find out. So magnitude will be 1 over 1 plus omega square tau square is the magnitude. Yeah, square root of that, and of course it will be the square root of that. So how, right? So this is the magnitude, and the angle is simply the tan inverse, and then you have this divided by this. So tan inverse minus omega tau, right? Okay. Now for different values, as we did in the Bode plot, yeah, for different value we can find out like this. Let us say omega square or tau square is equal to 0. Yeah, that really means omega equal to 0 basically. And in that case, the angle, the magnitude, or just write like this one. Okay, so we not write like this. Since we have both of them, magnitude and the angle here, so we write like this. Okay, so just g is like this one. So simply what we get g 0 is equal to, and we get here 1, right, 1, and then here we have tan inverse minus 0, and that becomes equal to angle 0 only, right? So we have like this. Okay, now let us say omega times tau is equal to 1. Yeah, and then what we get, tan inverse minus 1 minus 45 degrees. So we also saw there also. So g, let us say we call it I omega equal to 1 over tau now. So I 1 over tau, right? So now omega equal to 1 over tau, so that omega tau equal to 1. If that is the case, yeah, then we get is equal to omega equal to 1. So 1 plus 1, 2, 1 over root 2 we get, and then angle is minus 45 degree, right? Okay, now omega tau equal to infinity, right? So tau is a constant, omega will increase infinity, and in that case what do we get? We get here it is infinity, so value will be 0. So we get z here infinity is equal to simply 0, and angle we know that at there it is 100 minus 90 degree. Okay, so minus infinity tan inverse, so you get minus 90 degree. So this is how some of the points we have got. So we can try to plot it now based on this information, how it looks like. So here we have a real of G, and this is imaginary of G, where G I omega, that's what it means. Okay, so here we have 0, angle 1. So let's have this point, yeah, and this point will correspond to omega tau is equal to 0. Yeah, go like this. Okay, now next is minus 45 degree when omega tau equal to 1. Omega tau equal to 1, that is we have 1 over root 2, and then we have minus 45 degrees. So minus 45 degrees is here, and if this is 1, so from this is 1, so write 1 here. Yeah, so if it is 1 here, so 1 over root 2, let us say it could be somewhere here. Yeah, maybe here. Yeah, so from here to here is 1 over root 2, from here to here. And then when okay, and then we have 0 at minus 90 degree. So we have 0 here, value is 0 because radius will be 0 in that case, and minus 90 degree. So that what it means is it will be somewhere here, 0 magnitude, and then the curve should look like this. That really means it should go like this. Yeah, so because the value here is like this. Yeah, so this is how we got the initial points. We can take more points if you would like, and you can insert 2 points, one here, and you will get the rest of the points. But if you do more analysis, you will get something like this one. This will be a half circle like that, where from omega you are moving this way. From omega equal to 0, you are going to omega equal to infinity, and this is the point where you have omega tau equal to 1, right? This corresponds to omega tau equal to 1, and this corresponds to omega tau equal to infinity. So this is how it is going like this. We can also estimate or try to guess how this curve look like based on the equation also. So we can say that this is a form of x minus I y, like this, right? Where this is x and this is y, right? Okay, now, so that really means that what we are plotting here, these points are nothing but the we are okay, not like that. I think you have to write x plus I y, where y will be negative, included the negative sign, right? Okay, so now this is or let's call it from here to here is I y. Yeah, okay. Okay, now what kind of equation is going to fit, or try to guess the equation that it will be, or it will be part of that. Yeah, so what I mean to say is we have this one x equal to like this. Yeah, so we can try here also. We can see the if that is a thing, looks like it is a semicircle, somewhere here in middle will be half, right? So we can also test whether this point is really the center of the circle. So we can say here x plus I y, where x equal to this, so I y equal to minus I omega tau over 1 plus omega square plus tau omega square times tau square. So x minus half square plus y square. If this is a circle, the equation of the circle will be look like this one, x minus half square plus y square, and here what we get is 1 plus, yeah, so 1 plus omega square tau square, right, minus half square, right, plus omega square. So sorry, y square, y is minus omega tau over 1 plus omega square tau square, right, and square. Okay, what we get? We get here, this will be 2 minus this, so we get 1 minus omega square tau square divided by 1 plus omega square tau square, plus here we get omega square tau square divided by 1 plus omega square tau square square. Yes, okay, equal to 1 plus omega square tau square square, and here we will get here, from here we get 1, then minus 2 omega square tau square plus omega 4 tau 4, then plus omega square. Okay, remember we have also 2 here, yeah, so 2, so we have to get 2 in this case, so 2 here, here, so we have 2 also here, yeah. Okay, so we have a 2 like 2 to 4 basically, sorry, 2 square also, so we have 4, 1 plus this one, and then here we have to add 4 of it, so 4 omega square tau square. Okay, and then what we get here, this is minus 2 and this is plus 4, so this becomes plus 2 basically, and that makes it simply 1 over 4, and then you have 1 plus omega square tau square square over 1 plus omega square tau square, and is equal to 1 over 4 equal to half square. So what you get is equation. What equation? The x minus half square plus y square is equal to 1 over 2 square. So this is the equation of a circle, and hence that's what it is representing. Yeah, this is the arc of a circle, but actually this gives you the full circle, right? This gives you the full circle because we have squared it, you know, so it has a minus sign here, but actually we have a squared. So hence the half of the thing are actually not on the curve, but this gives you the full curve, but actually the semi-circle is the one will be the right curve. Yeah. So this is the polar plot for the first order system. Similarly, we can look at the second order system, and second order system looks like Gs equal to omega n square over s square plus 2 zeta omega ns plus omega n square, and hence gi omega is given by simply omega n square divided by minus omega square plus 2 zeta omega n omega I plus omega n square, and which is equal to, we bring it down, and then we can have this one, so 1 minus omega square, right, so over omega n square plus, just a minute, so 1 over we have to write, so 1 over, and we have 1 minus omega square over omega n square, and then not a square, sorry, okay, plus you have I 2 zeta omega over omega n, right? Omega over omega n, right? Okay, so this we have seen already earlier while drawing the Bode diagram. Here also we can see once more, and depending on the value we can write. So if G, we can write here 0, right? So when you have omega equal to 0, or basically what we mean is omega over omega n equal to 0, that's what we mean, right? And in that case, what do you get? The value, you get this. So omega to 0, you get and 0 here, so you get just 1. The value will be 1, magnitude will be 1. If you put 1 here, 0 here, and becomes 0 here, so only 1. And the angle will be, we know that the angle is also, so look at that. Here the angle is also 0. Why 0? Because this is equal to, we can also write, will be simply 1 minus omega square over omega n square, and then we have plus minus I 2 zeta omega n omega over omega n, yeah, omega n divided by 1 minus omega square over omega n square plus 2 zeta omega over omega n square, right? Okay. This will be like this one, and hence if we put omega equal to 0, then this terms becomes 0, this terms becomes equal to 1, yeah. So hence what we get? We get 0 over 1, and hence you have 0 term like here, yeah. Okay, done. Now G equal to infinity, we put it infinity, right? So omega infinity or I infinity, put like that, yeah. In that case, what happens? So we can look at this. When omega is infinity, so this will, so here this term will be very a small comparison with this term, and this term will be a small comparison with this term. So simply what we have is 1 over, you get 1 over minus omega square, so we get like this, 1 over omega n minus omega n square over omega square, where omega is very very big, yeah, and then minus sign here, right? So this is equal to like this, minus sign, meaning that this will be minus 180 degree. That we have seen while plotting the Bode diagram as well, that we get the minus 80 degree. So what we get is 0, and we get minus 180 degree. So you can also see here, when omega goes to infinity, automatically we will have denominator tending to infinity, and hence this will be 0, and hence you get that. So this is how it looks like. Now in between, if omega equal to omega n, so G I omega n, so omega over omega n equal to 1, that's what it really means. So G I omega n will be, in that case you have simply this term will be 0, and what you are left with this one. So what you have is simply I2, right? So I2 zeta, that's it. Omega over omega n is 1, so you have this one, or equal to 1 over 2 zeta, and minus I simply, right? We'll have that. Okay, so minus I is simply 1 over 2 zeta r minus 90 degree. Yeah, that we have seen that when omega equal to omega n, we have minus 90 degree. So we have roughly the values basically. So and accordingly we can draw something, something we can do. And what we get, omega equal to 0. Omega equal to 0 means real axis, in the positive real axis. Yeah, this is the real part of zi omega, yeah, this is imaginary part of gi omega, yeah, and then we are varying omega, we are going to plot it. Now the value is 1 when you have so on the real axis, positive real axis. So that really means 0 angle. So from here it's a 0 angle here. So this is value 1. So we plot it like this one. So this is done. Second thing is it says 0, value is 0 at minus 180 degree. So value is 0. Yeah, and you can also write that here omega equal to 0, and this corresponds to omega equal to infinity, right? And then it's in minus 80 degree. Minus 80 degree means it has to be something like this. Yeah, it will be little bit like this. Yeah, here. Okay, so it has to be like this one. Yes, because it is 180 degrees. So the point will be on this axis. Yeah. Okay. Or you can assume this when it is 0, very small value, but on the this line, on the real axis, negative line. Okay. So, but very close. It is on 0 only, but it should go like this. Okay. Now next is the angle 90 degree, minus 90 degrees. Minus 90 degree is this one, right? So 0 degree, 90 degree, 180 degree, or minus 180 degree, and 0, minus 90 degree, minus 180 degree, right? So this is minus 90 degree, and we have to plot 1 over 2 zeta. So wherever it comes, right? So this is 1 over 2 zeta. Yeah. Okay, and now you can think that this will be something like this, right? So something like this. This is how the plot will be. For different value you have different. Now you can see that if zeta equal to 0.5, you have just value equal to 1. Yeah. So this is 1 here. So let's call 1 here like this. Yeah. So if this is 1, the value will be from here to here, it will be 1, from here to here. Right? So zeta equal to 0.5, when here to here the value is 1. Yeah, that's what it meant. And so on. When zeta is 0, then value becomes infinity. Yeah, so for zeta equal to 0, it will go very much down, right? So yeah, so let us say this will be zeta equal to 0.1, will be larger, and so on. This, let us say this is zeta equal to 0.4. Yeah, and so on. So this is how the polar plot for the second order system will look like. Yeah. Given the plots, if you are asked what will be the maximum, the amplitude, yeah, so you can find it by the radius is the one that decides. So for example, on this curve, radius is maximum here. Yeah, so maybe this reduces, I mean, again, this approximately I'm drawing, not necessarily it has the correct values, but this is the trend it shows. So let us say if you have to find for zeta equal to 0.5, you want to know at what angle or what is the phase when you get the maximum value, or what is the maximum value you get. Yeah. So in that case, what you do, you are going to have a tangent line. So you draw a circle, right? So you draw a circle, for example. Let us say you are drawing a circle, and whichever circle is the one which gives you the maximum, right? So could be something like this. So this will be, let us say, if your circle looks like this. Okay, let us say your circle looks like this one. What you see that at this point it is making a tangent. That really means it tells you the maximum amplitude or magnitude you are getting at this point, and that will give you the resonant value, what the maximum value that's possible, and this angle will give you the phase. Let us say call it phi r, yeah, and phi r, it will give you the value from here to here, and corresponding omega will give you omega r. Omega is resonance, right? So from this circle, these polar plots, you can also find out the resonant frequency. Resonant frequency is the one which gives you the maximum amplitude or magnitude. Yeah. Next is what is called Nyquist plots. So Nyquist plots are basically the polar plots only. Yeah, so this is equal to polar plots. Polar plots for omega greater than minus infinity to infinity. So in polar plots, we have seen that polar plots typically we had omega positive only. We have from 0 to infinity, but the Nyquist plots are for minus infinity to infinity. So this is what the difference is. So basically there is no actually much difference. Both are the same thing. Only thing is if your polar plot, for example, for a first order system, we looked at polar plot was something like this. Yeah, so from one semicircle goes from one goes like this one, right? So this one was polar, right? Polar. And Nyquist will be simply you have to include the mirror image as well. So you have one which go like this, and it will also go up, also go like this. So you have mirror image. So original polar plot you have here, which goes like this one, and then you have this also. So this one is omega equal to 0, and here you have omega equal to infinity. Yeah. Again, from here you go the value of let us say somewhere here was omega tau is equal to 1, right? Okay, and similarly somewhere here you will get omega tau, let us say this is value, you get 1 over root 2, right? So So 1 over root 2 you got. Similarly here also you get 1 over root 2. Yeah, and that was corresponding to 45 degrees. So it was 45 degree. Similar point will be there. So 45 degree, and the value here will be minus omega tau equal to 1. So omega equal to minus 1 over tau. Yeah, and so on, right? So this is from omega, it is here this point will have omega also, and minus omega equal to minus infinity as well, and this is how it will be changing minus. So immediately here also it will be minus omega equal to minus infinity as well, right here. Yeah, okay, so this is how it will go, like this. So this is what this is Nyquist plot. Nyquist plot. So what is the difference? Plot plot, take the mirror image of that and you get that Nyquist plot. Just you have to add the mirror image. Okay, so equal to polar plus its mirror image about the real axis. That's it. It's the same thing. Yeah. Similarly, we can look at this is a first order system. So for second order system, we can see that. So for second order system, we had a polar which looked like something like this. We had from here started and went like this one. Let us say you looked at like this one. So this was the polar for second order. We know that this point is 1 over 2 zeta, right? And this is 90 degree. Yeah, this is omega over omega n equal to 0. This is omega equal to omega n, right? And here it was omega equal to infinity. Yeah, so this is what the polar look like. Yeah, so the Nyquist will be just we add the mirror image here. So this will be like this. So this is real, this is imaginary, and we first draw this exactly this one. So here from here it starts, let us say goes like this. Yeah, so same thing we have done, and then mirror image of that. So we get the same thing here. Right. Yeah, so from here to here it goes like this, and then it will go like this as well, and it will be the same value. Here it will be say omega equal to omega n. This is omega equal to 0. This point will have both omega equal to infinity, omega equal to minus infinity, both. Yeah. This point will be omega equal to minus omega n. Yeah. And so on, from minus infinity, minus omega n, it goes to 0. So just the mirror image if you include, you are done. So this is what the Nyquist plot is. Nyquist plot is very important, you know. So we are going to actually study the stability criteria. There is something called Nyquist stability criterion that we will do the next. But before that, we have to understand from where it comes. What is the meaning of that? Yeah. So little bit difficult mathematics involved. Okay. So we have to. We are not getting into those difficult mathematics anyway, but we will see some example. We will see to actually verify or understand what is the meaning of the Nyquist stability criteria.